Hey everyone, thank you for coming. Let's say you install some simple app on your phone. For example, a flashlight app. It does exactly what you expect until at some point it asks for access to your contacts. Nothing breaks, there's no alert, it's not obviously malicious, it's just unexpected. In the cloud, we look for the same kind of signal when a widely deployed process suddenly asks the cloud for identity when it never needed cloud credentials before. That moment isn't dramatic, but it matters. Because in a healthy cloud environment, access to identity is something extremely predictable. And when something predictable suddenly isn't, that's a signal worth paying attention to. So in this session, I'm going to present one of the methods that we use to hunt anomalous and potentially malicious credential access in cloud environments. The method is grounded in a precise understanding of how cloud workloads normally interact with identity and metadata services, what's common, what's rare, and what simply shouldn't happen. I'll explain how we leveraged cloud-scale telemetry to build a process prevalence graph, and why focusing on rare behavior in common software allowed us to uncover hidden abuse patterns and 0 days, even when we didn't yet know vulnerability exists. But before we begin, just a quick introduction. My name is Hila Ramati, and I'm a threat researcher at Wiz. This project was a collaboration with Gili Tikoczynski, who was also part of our research team. Gili couldn't be here today, but he sent me with strict instructions to make sure you all leave this session slightly more paranoid than when you walked in. So let's get started. Starting with a bit of background, especially for those who might not be deep into cloud internals. So IMDS, or the Instance Metadata Service, is basically a small internal API that lives inside every virtual machine in the cloud. Its job is to give workloads temporary short-lived credentials and configuration data. So you can think of it as the cloud-native way for instances to identify themselves and securely access other resources in the cloud, like reading or writing to an S3 bucket, getting secrets from the secrets manager, and things like that without ever hard-coding credentials or storing long-term secrets. For example, from inside an EC2 instance, an application can send a simple HTTP request, and IMDS will return a temporary token tied to that instance's identity. So it's important to emphasize that IMDS isn't some obscure or risky feature. It's actually the correct and recommended way to do things in the cloud. Every major cloud provider, Azure, GCP, and AWS, relies on a metadata service like this and ships their official SDKs, agents, and init scripts with built-in IMDS integration. It's documented in all their guides as the right way for instances to authenticate. As a result, IMDS access is extremely common and expected in cloud telemetry. Hundreds of processes access it every single day. And that's exactly what makes it such an interesting attack surface. Not that it's unusual, but that it's everywhere, trusted and deeply embedded in how cloud identity works. So we've seen IMDS abuse in several real-world cloud breaches, and almost every time, the root cause isn't IMDS itself, but an application that unknowingly acts as a proxy to it. One common example is an SSRF vulnerability, which occurs when an attacker tricks a vulnerable application into sending HTTP requests on their behalf. So in a traditional on-prem world that might get you access to an internal service or a dashboard that shouldn't be exposed, but in the cloud, the impact is much greater because every instance has a metadata endpoint sitting at a fixed internal IP address, and a simple SSRF suddenly becomes a direct path to cloud credentials, and from there to privilege escalation. Cloud providers have introduced several mechanisms to try and make IMDS abuse harder. For example, Azure and GCP both rely on a specific metadata header to be included in every request, Without that header, IMDS simply won't respond. AWS took a slightly different approach with introducing IMDS v2, which adds a session token. The instance has to first request that token using an HTTP put call, then include it in a follow-up GET request. These protections are very good because most simple SSRF payloads can control both HTTP methods or multi-step request flows. But this doesn't eliminate the problem entirely because adoption isn't universal and many workloads still use old configurations which allow IMDS v1, which was the simple, unauthenticated HTTP GET request access. And as always, attackers go after the easiest target available. To show why that matters, let's look at one of the highest profile real-world examples, the Capital One breach. In that case, an attacker exploited an SSRF in a web application running on AWS. Using that SSRF, they made HTTP calls to IMDS v1. And because IMDS v1 didn't require a token or any authentication, they could directly query the relevant endpoints and retrieve temporary IAM role credentials. Now, unfortunately, those credentials belonged to a privileged role with access to sensitive S3 buckets. Once they had those keys, the attacker didn't need to touch the compromised host again. They could directly use AWS API calls to list and exfiltrate customer data. So that simple SSRF combined with IMDS v1, which was at the time just IMDS, led to one of the largest cloud breaches ever recorded, with over 1 million records exposed. The incident completely changed how the industry thinks about IMDS and is now the main reason AWS strongly recommends enforcing IMDS v2. So going into this research, we already had visibility into a huge amount of data, thousands of cloud environments with runtime and network telemetry. Across that data, we had seen IMDS abuse show up occasionally, but always as part of a post-incident investigation. Those were valuable, but by definition reactive. What we wanted to do here was different. We wanted to create a systematic, data-driven way to surface this entire class of abuse, even in cases we hadn't seen before, and ideally before they turn into breaches. So, learning from those previous cases, we had noticed a common theme. Legitimate software behaving in ways it usually shouldn't. That led us to a pretty simple hypothesis. If a process that normally never talks to IMDS suddenly starts doing so, something's off. We'd seen exactly that in the Capital One breach, where a firewall process, which is a completely legitimate binary, unexpectedly accessed IMDS. So instead of starting from a known vulnerability or exploit technique, we flipped the problem around, using cloud scale telemetry as a behavioral baseline, then looking for deviations from that baseline. So as I said, we had a pretty simple hypothesis. If a process that normally never talks to IMDS suddenly starts doing so, that's suspicious. Maybe it's a legitimate library update, or maybe it's exploitation. But either way, it deserves a closer look. So to test that, we collected telemetry from thousands of environments, tracking which processes access IMDS in runtime. Using that data, we built what we call a process prevalence graph. So each column represents a process that we observed accessing IMDS somewhere. The total height of that column is its overall prevalence, how common that process is in the dataset. The color breakdown shows behavior. So pink means environments where that process did not access IMDS, and blue means environments where it did. So you see here some columns are almost entirely blue. Those would be processes like Amazon SSM agent or Cloud Init or various cloud SDKs that are supposed to talk to IMDS all the time. And some columns are a mix of pink and blue, and those would be processes like the more common executables, like Python or Bash or Node, that get used for all kinds of tasks. Some of them should talk to IMDS, some of them shouldn't, so they naturally end up with a mix of pink and blue. But the really interesting columns are the tall columns, with just a tiny blue slice. That pattern tells us two things. A, this process is widespread, so it's probably legitimate. And B, only in a very small subset of its instances it ever accesses the metadata service. That is a very strong anomaly signal. And when we zoom in on the most interesting part of the graph, the bottom processes sorted by IMDS access, this is what it looks like. So each process here is widespread and legitimate, found in a lot of environments. Those aren't shady binaries or unknown payloads. These are perfectly legitimate, widely used tools. And that anomaly, that tiny IMDS activity sliver, is what made us ask, why would a document converter or an analytics database ever need access to cloud credentials? Why would a flashlight app on my phone ever need access to my contacts? And after some digging, we came across some very unexpected stories, including a vulnerability and a live SSRF exploitation attempt, which leads me to our case studies. So the first anomaly that caught our eye came from Pandoc. For anyone not familiar, Pandoc is an open source document converter. You'll find it in CI/CD pipelines, report generators, PDF exporters, even notebook environments. And under normal conditions, it has no reason to access IMDS. So when we saw one environment where it unexpectedly did, we asked ourselves, what would an attacker have to do to make Pandoc talk to IMDS? When we investigated, we found that in that specific environment, Pandoc wasn't being run as a CLI tool, but it was embedded in a web service. That web service allowed users to upload HTML and have it converted into other formats like Markdown. Now, in HTML, an iframe is a tag that tells the renderer, or in this case, the server, to fetch the content of a remote URL and have it embedded in the document. So from an attacker's perspective, this becomes straightforward. If I could submit HTML, I include an iframe that points to an internal address, for example, the metadata service. Pandoc then fetches that URL on my behalf. That's basically classic SSRF. But in the cloud, it means Pandoc is now asking the cloud for identity. And if this had been running with IMDS v1, this would mean that Pandoc was fetching valid temporary credentials, effectively handing the attacker the instance's IAM role. Now, this behavior corresponds to a known vulnerability in Pandoc's HTML renderer, but interestingly, the Pandoc maintainers categorized it as expected behavior rather than a flaw. And the fix was simply add a warning in the documentation, meaning the most up-to-date version is still vulnerable. In other words, the web service itself is vulnerable to SSRF, to IMDS. Now, fortunately, this specific environment has a really good cloud posture. So IMDS v2 was enforced, and since IMDS v2 requires a session token, the attacker's simple iframe-based GET request couldn't complete the required handshake. But the outcome wasn't guaranteed, and this could have easily turned into a full breach. Now, this finding validated our methodology, because we didn't start by looking for a vulnerability in Pandoc. We didn't even know what Pandoc was. We just looked for software that had no business talking to IMDS, and this anomaly just popped out of the graph. That same graph later popped another anomaly in a different tool, in a different cloud provider, which leads me to our second case study. So the second case that caught our eye came from ClickHouse. So for anyone not familiar, ClickHouse is a widely used analytics database. It's found in a lot of environments, and it almost never accesses IMDS. So when we saw one environment, this time in a GCP deployment, where it unexpectedly did, we asked ourselves the same question. What would an attacker have to do to convince ClickHouse to talking to IMDS? So after some digging in ClickHouse's features, we found one that's very powerful and very relevant here. It allows users to pull the content of a remote URL into a table. And it's a great feature for analytics, but from an attacker's perspective, it's also an SSRF primitive, especially in the hands of an untrusted user or used in multi-tenant systems. And another really interesting thing here is that this feature, thank you ClickHouse, not only allows control over URL, but it also allows control over headers. And if you remember, both Azure and GCP require a specific metadata header to be included in accessing IMDS. So from an attacker's perspective, again, if I can submit a query like this and control both the URL and headers, I can potentially extract credentials. Now, in this specific environment, the ClickHouse was running under a restricted service account, so there wasn't much to steal. But again, the outcome wasn't guaranteed, and this could have easily turned into a full breach. But the point here isn't the specific feature or bug in ClickHouse, but it's how we found it. We had no other signatures, no prior intel, just looking at the graph, that same graph that surfaced Pandox vulnerability, surfaced this vulnerability in a completely different tool, in a different cloud provider. So to take a step back from the case studies and wrap things up, the key point here isn't the specific exploitations I showed. I mean, they're valuable, but they're really just examples. It's about hunting anomalies in a well-understood environment. If you have a really good understanding of how your environment is supposed to behave, deviations become a very high-quality signal, even without other vulnerability knowledge. Now, the second thing is about timing. Vulnerabilities are being tested and exploited much faster, often before they're named, documented, or well understood. So if detection relies on vulnerability names, signatures, or mature intelligence, it will always be late. This approach doesn't rely on any of that. It simply relies on having a good baseline of expected cloud norms than looking at deviations. So this is how we went from not knowing what Pandoc was to finding a vulnerability and a live exploitation within a couple of hours. And this doesn't stop with IMDS. That same approach can be applied in access to any sensitive service, path, or API. It's also not about scale. You can do it analyzing one environment or thousands of environments. Define what's normal, then look at the outliers. That's where the cool behavior usually lives. And if there's one thing I want you to take from this, is that high quality anomaly detection starts with a really good understanding of how your environment is supposed to behave. And that understanding is what lets you move faster than anyone, even attackers. So thank you everyone for listening. And if you have any questions, I'll be right outside so you can catch me.